Welcome back to Orangian Maritime Academy, the subject of Applied Heat Marine Engineering Management level. Under the title of Process, Question 1, you're going to solve Tutorial 1, which is a combination of isobaric, isochoric, and isentropic processes. Question 1, December 2011. Ideal gas in a cylinder is cooled at constant pressure from a temperature of 1200 degrees C to a temperature of 800 degrees C, and then further cooled at constant volume from 800 degrees C to 500 degrees C. The change in specific entropy in the second process is minus 3.326 kilojoule kilogram Kelvin. After being cooled, the gas is compressed isentropically to the initial pressure at a temperature of 577.3 degrees C. So the first part of the question asking about to sketch the processes on PV and TS diagrams. So for the management of solving the question, the most important thing is extraction of all the data and values from the context of the question and put it on your exam paper so you can have all the data in front of you. You don't need to go back to the question over and over again, so it will save a lot of time for you. So by going through the question, we can see that we have got three processes. Process 1, isobaric process from T1 to T2, cooling, and then process 2, isochoric process, which is a cooling process from T2 and T3. So during this process, the change in entropy is minus 3.326 kilojoule per kilogram Kelvin. And then we have got process 3, which is isentropic process, a compression process from T3 to T4, and then going back to the initial pressure, that means P4 is equal to P1. So we start with PV diagram process 1. So as process 1 is isobaric process, so we consider a constant pressure dotted line, which is P1. So now we draw from state 1 to state 2. So this is the path of the isobaric process, and this is the direction. So the direction is to the left because the law of the isobaric process is Vt equal to constant. That means V is proportional to T. So at constant pressure, if temperature decreases, then we are going to have the volume decrease. So that's why this is the direction of the path of the process. So I write down over here isobaric. So now we draw the isobaric process on this diagram as it is at a constant pressure. So I'll just draw a constant CP curve, which is equal to P1. So now the path of the isobaric process from state 1 to state 2. So this is the path of the process and this is the direction, because the temperature is decreasing, isobaric. So now we go to the second process, which is isochoric process. So isochoric process, that means constant volume. So from 2 we just make a vertical dotted line which shows a constant volume. So over here, from state 2 to state 3, we draw the path of the isochoric process. This is the direction of the path, isochoric. It is downward on the constant volume line because the law of the isochoric process is Pt equal to constant. That means P is proportional to T. So as T decreases, so pressure is going to decrease. So this is the isochoric process. So we want to see how would be the isochoric process on TS diagram. So as it is happening at a constant volume, so we need to draw the curve of constant volume. So this is CV. So you need to remember that the constant volume curve, the slope is higher than the constant pressure volume. So now we draw the isochoric process. This is the path from 2 to state 3. So this is the path and this is the direction of the path. This is isochoric. So now the third process. The third process is from state 3 to state 4. State 4 is lying on the constant pressure line, that means P1, because the question is saying that the end of the isentropic process is going to be P4 equal to P1. That means going back to the initial pressure. So this is the path of the isentropic process and this is the direction of the path. That means the pressure is increases, and as a result of increase in the pressure we have got decrease in the volume because of the law of the isentropic, which is PV gamma is equal to constant. So there is a inverse relationship between the pressure and volume. Now we will see how does it look like on the TS diagram. As it is isentropic process, that means it is happening on a constant entropy line. So we are going to have the process from 3 all the way to the point 4. So stage 4 is lying on the constant pressure Cp equal to P1 and P1 is equal to P4. P1 is equal to P4 and this is the direction of the path, because as a result of increase in the pressure we are going to have increase in temperature, and basically it has to reach to the point 4, which is the intersection of the vertical line with the Cp curve. So the second part of the question is asking about the value for Cv, Cpr and gamma. So part B of the question, asking about CV, CP, R, and gamma. So we start with CV. So to get the value for CV, we start with the isochoric process, and we know that the delta S is equal to CV natural log of T2 over T1. So this is the formula for change in entropy for isochoric process. Isochoric. So using this formula, we will write it down for our isochoric process from state 2 to state 3. So we will write down that the delta S to 3 is equal to CV natural log of T3 over T2. So now we put the value. We know that the change in entropy for our process number 2 is minus 3.326. So we write it down here, minus 3.326 is equal to CV natural log of. So we have T3, which is 773 over T2, which is 1073. So we can write down that minus 3.326 is equal to CV times, so then that natural log is minus 0.328. So from here we get CV is equal to minus 3.326 divided by minus 0.328. So from here we get CV equal to 10.14 and the unit is kilojoule, kilogram, Kelvin. So now for CP, for getting the CP, so we need to find out the isobaric process. So we know that the general formula for isobaric process is delta S is equal to CP, the natural log of T2 over T1. So you need to remember this formula, and this is for any isobaric process. So now we put the value for every part. So in continuation of the solution for BI, we are looking for CP, and we just write down the general formula, which is delta S is equal to CP natural log of T2 over T1. So this is for isobaric process. The point is that now we have got delta S23. We have got the value for delta S23, but the point is that we cannot use it because that is for the isochoric process. So we are going to use this part of the sketch from 2 to 4, and that is delta S 24. As you can see that delta S23 is equal to delta S24. So we use this, so delta S23 is equal to delta S24. And the point is that this path of the 2,4, that is isobaric process because it is lying on the curve of constant pressure. So delta S23 is equal to delta S24, and this is equal to Cp natural log of T4 over T2. So now we put the value, so we have got minus 3.36 is equal to Cp natural log of 850.3 over T2, which is 1073. So now we can get Cp. So Cp is equal to minus 3.36. So that natural log is equal to minus 0.233. So from here we can get Cp is equal to 14.43 kilojoule kilogram Kelvin. So this is a part of the answer. Now we want to calculate R. So R is equal to Cp minus Cv. So 14.43 minus 10.14. So this is equal to 4.3 kilojoule kilogram Kelvin. Now what remains is gamma. So gamma is equal to Cp over Cv. So we have got Cp 14.43 over 10.14. So from this ratio we can get gamma is equal to 1.41, and that is a part of the answer. So now the B2 is asking about the change in specific entropy during a constant pressure process. So constant pressure process, that means that isobaric process. So we write down the formula delta S 1, 2 is equal to Cp natural log of T2 over T1, and this is equal to, now we have got Cp so the Cp which we have calculated, so we are going to write down 14.43 natural log of 1073 over 1473. Now from here we get delta S12 is equal to minus 4.56 kilojoule kilogram Kelvin. So the last part of the question, it is calculation of the work transfer. So we write down over here that W 34 is equal to R T1 T3 minus T4 over gamma minus 1. So now we put the value, that means it is 4.3, which is for R, times 773 minus 850.3 divided by 1.41 minus 1. So from this we get W 34 is equal to minus 810.71 kilojoule. So as it is minus, that means work on the gas. So now the solution is complete.